Hi students, this video is on crust types and density. One of the things that you'll learn in this video is that the crust is made up of two types of crust, oceanic and continental. There are different crust types that have different densities, and that changes the way that they interact on plate boundaries. And lastly, that there are different ages to the different crust types. So that those are the three learning goals for this lesson. Let's go over the two different types of crust. First, there's an oceanic crust, and the oceanic crust is very, in its name, the crust that is over the ocean. This crust is thin and rather dense when compared to what's called the continental crust. So the oceanic crust is very thin relative to the continental crust and is dense. Even though there's less of it, it actually is a denser crust overall because it is a little bit more compact. If you were to compare the density values, the density of the oceanic crust is something like 3.0 grams for every milliliter of volume, and then the density of the continental crust is something like 2.7 grams per milliliter of volume. So not a huge difference, but enough that, well, if you put them both together, then one is going to float on top of the other. And that's what you're seeing here as the oceanic crust dives underneath the continental crust that's coming this way. And when that happens, you usually get a little ocean trench in here. And additionally, as the crust goes underneath the other plate that's coming over with the continent on it, you will get a process called subduction. And down here, you'll actually have the melting of the oceanic crust. Another important part about that, I was just mentioning, but to show it a little clearer, is that when you have the oceanic crust all together moving as a plate, it will proceed underneath a continental crust. And when it does that, it again melts, and some of the magma will then come up through the continent. You can get a volcano. But greater than that is that the crust density is the thing that's driving those activities. This crust would be moving this direction. This crust would be moving that direction. They're both continental crusts, but because they're less dense, they sit on top of the oceanic crust, and the oceanic crust then dives beneath them. And that's driven by the magma that's coming up right about here. The magma that comes up through the mantle, which is basically liquefied rock that's coming up through the oceanic crust, will break through and push these plates apart, causing one to go this way and one to go that way. And as that occurs, it is then pushed underneath the respective continental crusts that sit on top. So this might beg the question of, well, if the oceanic crust is always spreading, and it always goes underneath the continental crust, does the continental crust ever change? And that actually is an interesting fact, that the continental crust that sits on top, because it's less dense, will almost never get recycled. It will never go underneath oceanic crust. So the continental crust is almost the same crust that we've had on planet Earth since the continental crust was formed. What you can see here in this map with the false color here is that we're showing how old the Earth's crust is based on core samples that have been taken at different areas. So they take little samples from different areas on a ship. They use a ship to go around and pull a sample out of the sediment of the ocean, and they test it to see how old it is using a variety of methods. But what they find is that the closer you are to these mid ridges, this one here is called the Mid-Atlantic Ridge. This is called the East Pacific Rise, or the Pacific Rise. This is where the plates are spreading apart, and you get new Earth forming. So the youngest Earth is the red line that goes right around where all those kind of Earth splitting areas are. And the further away you get from a rise or a divide like this, the older the Earth gets, the older that oceanic crust is. And so you can see here the age of a lot of the Earth that's beyond the rise, you get in the this green color, which is around 100 to 140 million years. The oldest crust being kind of here in the Mediterranean Sea, so some very old crust in there still. And again, that's just taken by core data. An example of this phenomenon can be seen in this little animated graphic here, where as you click this little time indicator, you can change the amount of time that's been going on, and you see that as you go through time, the longer time goes on, the Earth in the middle starts to spread, and you get new Earth formed. So the oldest Earth is the red line here, or I guess the brown line really, and the youngest Earth is the yellow line right there, the yellow block. So as I roll that back, where the convection happens right underneath and the ocean starts to split apart, you get new Earth created as time goes on. So the ocean crust is younger than continental crust overall. Continental crust never really gets recycled. So the oceanic crust diving beneath continental crust keeps the cycle of the oceanic crust and the ocean's floor in more of a rapid recycle than anywhere up on the continents. And necessarily, if some of the crust gets destroyed, it has to be made somewhere, and that's where the these different rises come in. There's a lot of earthquake activity around those rises, but it's not nearly as violent as it is on the places where the Earth actually gets sucked down, the oceanic crust gets sucked down and subducted. But we'll learn about that in another video.